Functions for financial rules in banking. This lesson covers how to code financial rules and business logic using Python functions. You will discover why functions are essential in automating, testing, and enforcing policies in real-world banking systems. By the end, you will know how to build, debug, and test banking rules for fraud checks, transaction limits, fees, and more. Functions make your code reusable, allow for clean business audits, and help ensure regulatory compliance. All exercises use realistic banking transaction data so you can practice practical use cases. Running the cell now. We import the warnings library to filter out runtime warnings. We ignore warnings for a cleaner learning experience. We import pandas to handle tabular banking data. We import NumPy to work with numerical values for transactions and random data. Running the cell now. Remember, consistent imports help teams avoid mistakes and encourage reproducible results. Understanding the core data for banking business rules. Transaction, customer, and account tables record real-world operations. Each row in a transaction table is a transfer of value with metadata like time, type, and amount. Beginners sometimes mix up debit and credit, or forget to handle negative values. Columns like customer_ID link records between datasets. Financial rules must respect the data structure to avoid errors. Always check your data for missing or illogical values before building any rules. Running the cell now. Business rules need real transaction data. Let us create some synthetic transactions for our functions to operate on. Set the random seed to 42 for reproducible results. Always fix the random seed so your colleagues get the same sample data. We create a data frame of 1,000 random transactions. We define the number of transactions. We define the number of unique customers. Each transaction gets a unique identifier. Each transaction is assigned to a random customer. We generate realistic transaction amounts using a normal distribution. Each transaction is labeled as either debit or credit. We assign random banking channels like ATM or online. We generate timestamps spaced by the hour. Show the structure of our table as rows, columns. Display the first 3 transactions for a quick preview. Running the cell now. This output shows a synthetic dataset of 1,000 banking transactions across 200 customers, with 6 key columns including transaction metadata like amount, type, channel, and timestamp. Notice each transaction has a unique ID and is associated with either a debit or credit type, reflecting real-world transfers. This confirms we have a realistic base table to practice distinguishing and handling transaction details accurately in business rules. Try adding new transaction underscore types or changing channel options. What business policies might apply to these new categories? Banking rules often depend on customer segment or region. Let us create a basic synthetic customer table. Create a list of customer IDs in a consistent format. Put together a data frame holding customer details. Each customer has a unique identifier. The first 150 are retail, and the next 50 are business customers. We split customers into metro and regional areas. Check the dimensions of our customer table. Preview the details of the first 3 customers. Running the cell now. The output shows a customer data frame with 200 rows and 3 columns, confirming the intended size and structure. Each row represents a unique customer with an ID, segment, mostly retail, and region, illustrating how customer data is organized to link with transaction records. This setup is key to understanding how customer attributes affect banking rules and transaction analysis. Segment-based logic is common for product eligibility and risk checks. Think of a rule for rural business customers. Let us create a third table with accounts. Different rules apply to savings and credit accounts. Build a synthetic accounts table relating customers to accounts. Generate unique account IDs. Link each account to a customer. Assign a random account type. Assign unique opening dates in 30-day steps. Show the total size of the table. Display a preview of 3 sample accounts. Running the cell now. This output shows the accounts table with 200 rows and 4 columns, confirming we have many accounts linked to customers. Each account has a unique ID, a customer ID, an account type, savings, check, or credit, and an opening date, which are essential for mapping transactions to real-world accounts. Notice the variety in account types, which affects how transactions like debits and credits are handled later in the lesson. Practice, write down 3 rules that only apply to savings accounts or to accounts opened after 2020. Beginner example 1, a simple minimum amount rule. Many banks block or flag transactions below a set minimum, for example for anti-money laundering or fee reasons. Let us design a reusable function for this, instead of repeating your logic everywhere. Running the cell now. We automate the minimum amount check by coding it as a function. This makes the rule testable and modular. Define a function that returns true only if the amount meets the threshold. Use a default threshold of 50.0, but allow the limit to be changed easily. Apply the function to all transaction amounts to get a true or false. See how each example transaction is flagged. Running the cell now. Here, the output shows the first 6 transaction amounts alongside a new column, *meets_minimum*, which indicates whether each amount meets the $50 threshold. Notice all these amounts are above $50, so the column returns true, confirming our function correctly flags transactions that meet or exceed the minimum. This demonstrates how encapsulating the rule in a reusable function helps apply consistent logic efficiently across your data. Can you modify this function for a different minimum, such as $25? Beginner example 2, customer-based rule with function. Some banks set special rules for business customers. Let us make a function that checks if a customer is in the business segment. Running the cell now. Write a function to check whether a given customer belongs to the business customer segment. Define a function taking a customer underscore ID. Look up the customer's segment in the customer table. Return true for business, false otherwise. If not found, return false. Test the function on a small set of unique customers. Print the result for easy verification. Running the cell now. The output shows the function correctly identifying whether each tested customer belongs to the business segment, returning true only for cust_0180. Notice how the function filters the customer segment and handles missing data safely, aligning with the lesson's goal to create a reusable rule for classifying business customers in the dataset. Try adapting this rule for another segment, like retail. Beginner example 3, channel restriction with a function. Sometimes a bank wants to block high-value transactions via POS terminals. Use a function to flag such cases for review. Running the cell now. Write a function for channel-based limits. Here, we filter out large POS transactions. Define a function that checks both channel and amount against a limit. Return true if POS and above the threshold. Apply to every row in the transactions table. See a few sample results for blocked POS transactions. Running the cell now. This output shows the first 8 transactions with a new column blocked_POS that flags high-value POS payments over $500. Notice all values are false because none of these amounts exceed the $500 limit, demonstrating how the function correctly identifies no need for blocks in this sample. This confirms our channel-based restriction logic is applied row-wise to the data frame as intended. Practice, adjust the limit and see how many more transactions get flagged. Intermediate example 1, function for transaction daily limits. Most banking systems set daily transaction count or value limits. Let us write a function to count transactions for each customer per day. Running the cell now. Let us build a Python function to count transactions per customer per calendar day. Extract only the date, no time, for daily grouping. Define the counting function for customer and date. Count all records matching the customer and date. Run the function for the first transactions customer and date. Print the results for clear customer and date feedback. Running the cell now. This output shows that customer cust_0103 made 2 transactions on January 1, 2024. The function successfully filters the data frame by both customer ID and date to count daily transactions, illustrating how banks can enforce daily limits. Notice how extracting the date-only part of a timestamp enables precise daily grouping, which is key for transaction monitoring. Can you write a similar function for total amount rather than count? Intermediate example 2, function to enforce weekly debit limit. Weekly debit caps are a core anti-fraud control. We will create a function for total debits this week for a customer. Running the cell now. Enforce a limit by totaling up debits for the last 7 days, including today. Define a function taking customer and date. Convert the date to pandas format. Calculate the start date, 6 days before. Create a mask for the right customer, debit transactions, and 7-day window. Sum all the debit amounts in this window. Pick an example customer to test. Pick the matching date for that transaction. Print out the calculated value in the business context for interpretation. Running the cell now. This output shows the total debit amount of $137.63 for customer cust_0075 over the 7-day window ending on the 1st of January 2024. Notice how the function correctly filters transactions by customer, type, and date range to enforce the weekly debit limit, which is key for fraud prevention. This confirms our function sums only relevant debit transactions within the sliding 1-week period. Try the function for different time ranges and compare with your own manual calculation. Intermediate example 3, function for allowed channels per account type. Not all products are meant for all channels. For example, a credit account may not allow ATM withdrawals. Let us design a function to enforce account type and channel rules. Running the cell now. Here is a reusable function enforcing that credit accounts cannot operate at the ATM channel. Define a function checking both account type and channel. Look up the account type for our customer. Return false if not found. Disallow ATM for credit account holders. Anything else is allowed. Test the function across several transaction records. Extract each sample transaction. Print out the customer, their channel, and if the channel is allowed. Running the cell now. This output shows the function correctly identifying allowed channels based on account type, returning false only when a credit account attempts an ATM withdrawal. Notice that for cust_0103, the channel is ATM and the function returns false, enforcing the rule we intended. For the other customers, the channels are permitted, demonstrating the function's role in filtering valid account channel combinations. Try modifying the rules, for example disallowing online for check accounts. Advanced example 1, flag multiple violations with composite function. In real banking, you need to check many rules at once and report which ones failed. We will build a function returning a dictionary of violations for a single transaction. Running the cell now. Combine previous single-rule functions into a composite. This is common for pre-processing or decision engines. Set up a function that takes a whole transaction row. Prepare an empty dictionary to hold the results. Record if minimum amount rule is satisfied. Check if the POS limit is violated. Check if channel usage is legal for the account type. Return the dictionary of results. Pick a transaction for a demo. Display the rule check results for a single transaction. Running the cell now. This output shows the violation flags for a single transaction, where each key indicates a specific rule and its Boolean result. Notice how the function returns a dictionary summarizing multiple checks, minimum amount, high position, and allowed channel, highlighting which rules passed or failed for that row. This approach lets you efficiently capture all rule violations at once, aligning with the lesson's goal to handle complex, multi-rule validation in real banking scenarios. Can you add one more rule, for example, based on region or segment? Try it out below. Advanced Example 2, Vectorized Application and Scoring for All Transactions. Real systems need to apply rules to millions of records quickly. We will vectorize and summarize violations for the entire data frame. Running the cell now. Let us apply the composite rule function across the entire transactions table and append the results. Apply the rule function to every row and expand the results into columns. Concatenate the results with the original data frame for easy visualization and reporting. Show an example output including the original columns and the new flags. Running the cell now. This output shows the first 8 transactions with their original amount and channel, alongside vectorized rule evaluation columns indicating if each transaction meets the minimum amount, minute_AMT, occurs at a high-risk POS, high_POS, and uses an allowed channel, allowed_channel. Notice all transactions pass the first 2 rules, while the allowed_channel rule varies, reflecting the code's intent to efficiently score multiple rules across the full data frame for rapid, scalable compliance checks. How many transactions violate at least one rule? Try counting the number of false flags. Advanced Example 3, Exporting Violations for Audit. Banks require robust audit trails of rule triggers. We will export all violations to a CSV file for review. Running the cell now. We need to extract only those records which violate one or more rules and save for audit or investigation. Subset the data frame to only those rows failing any of the rules. Set a file name for the report. Write the violations to a CSV file, no index column. Print out the count so the user knows how many will be reviewed. Running the cell now. This output confirms that 132 records failed to meet at least one of the defined rules and were successfully exported for auditing. Notice the non-empty violations data frame, which ensures the audit file captures all exceptions. This verifies the code's intent to create a comprehensive, reviewable audit trail for compliance checks. Opening the violations report for manual review and compliance audit. What information would your supervisor want to see in this report? What about customer details? Error handling example, defensive functions for data quality issues. What if customer_ID does not exist or data contains missing values? Let us improve our previous function to handle these cases and log warnings. Running the cell now. Always check input validity and pre-validate before looking up data. Define a safer version of the earlier function, which checks if input is none or missing. If the customer_ID is missing or not found, warn and return false. Print a warning and make the rule transparent when the customer cannot be found. Return false fail-safe outcome. Otherwise, look up the segment as before. Return true if the segment is business. Test the improvement by passing an unknown customer. Running the cell now. This output shows our improved function correctly identifies and warns about an unknown customer ID, returning false as expected. Notice how the warning message helps catch data quality issues early by flagging missing or invalid inputs, which is the core intent of adding defensive error handling in this lesson. This ensures downstream code can safely rely on valid customer segments without crashing or producing incorrect results. Try putting a none or a real customer_ID and see both code paths. If you are enjoying this hands-on learning, search for more rule coding tips on YouTube. Error handling example, handling non-numeric amounts and missing data. Bad data can crash rule engines. Ensure your amount fields are always numeric. We will build a safe function to handle inappropriate types or NaN values. Running the cell now. This is a defensive pattern. Validate each field before using it for business logic. Define a function which attempts to cast the amount as float. Use a try-except block so the function never crashes. Return true if the amount is not a NaN. Catch value or type errors cleanly. Return false instead of breaking your workflow. Run the validator on clean and dirty inputs. Check that a number returns true. A string returns false. NaN returns false. Running the cell now. This output shows the function correctly identifying valid and invalid amounts. It returns true for a numeric input, 10, and false for a non-numeric string, foo, and a NaN value. Notice how this validation prevents bad data from slipping through, which is essential for building a robust rule engine that won't crash when encountering unexpected types or missing data. Practice, add this check inside the minimum amount rule for safer processing. Best practices, naming, documentation, and testing. Use clear names describing what your function does. Add docstrings and type hints. Test on simple and edge cases every time you add or change a rule. Running the cell now. Let us improve our minimum amount rule with clean naming, a docstring, and input validation. Add type hints for function inputs and outputs. Document the purpose and expected behavior. Reuse the previous validator for safe numeric checking. Test with an amount equal to the threshold. Test with a value below threshold. Test with a string to check for safe failure. Running the cell now. The output shows the results of simple unit tests validating the function is _minimum_amount. Notice how the return values match the expected results, confirming the function correctly checks if amounts meet the minimum threshold and handles invalid inputs gracefully. This illustrates the lesson's emphasis on clear naming, documentation, and testing with both typical and edge cases to ensure reliable code behavior. Notice that clarity and checks make the downstream business work much easier and safer. Best practices, logging and traceability in rule functions. Banks must trace why a transaction was allowed or blocked. Add simple print statements or use logging for real-world code. Running the cell now. Here, key decisions are logged as print statements for traceability. We add a message when a transaction is flagged by the rule. If the channel and amount both meet the rule, log details and return true. Return false if the transaction is not flagged. Try flagging a high-value transaction. This will be flagged. Try a normal transaction, should not print anything. Running the cell now. This output shows how adding a print statement inside the rule function helps trace why a transaction was flagged. Here, a POS transaction over the $500 limit prints a clear message. Notice the function returns true only when the condition is met, providing both a trace log and a boolean for decision-making. This example highlights best practices for transparency in financial transaction rules. If you work in a real system, switch to logging instead of print for production. End-to-end challenge, detect debit rule breaches and warn customers. Let us combine everything. For each customer, flag all debit transactions exceeding a $500 daily limit. Output a warning per customer who violates this rule at least once. Running the cell now. Full workflow, summarize by customer and day, flag when above limit, and notify by print. Filter only debit transactions and sum them per customer and day. Add a column showing when debits go above $500. Collect a set of all violating customers, so each is only notified once. For each customer who triggered a breach, print a warning. Running the cell now. How would you notify staff to review these cases in the real world? Practice, tweak the threshold and display more transaction details if you like. Congratulations! You can now code practical financial rules. Practice with real banking rules and see how functions supercharge your compliance and automation. For more lessons and practical walkthroughs, look up Python rule engines on YouTube. Running the cell now.